What's the big picture we're looking at for the problems that we're going to be solving, these equilibrium problems? Well, there's going to be a general problem-solving procedure that we want to follow. And all of the problems that I'm going to present in this class, I'm going to follow basically the same steps. I'm going to make sure that I'm labeling the steps as we go. But the problem-solving procedure is going to give us a nice recipe, so to speak, of how to solve any of these equilibrium problems. So 1, we need to read the problem. What are we actually trying to do in this problem? So the first step is given. So reading through the problem, what information is given to us that probably is going to be pertinent in solving the problem. So here, a given might be the mass of some object, or it might be the distribution of weight of some object. It's some information given in the problem that might not make it into the free body diagram, but is still going to be important. Maybe there's a spring involved and we need to know what the spring constant is for subsequent calculations we're going to need to do. So it's often going to be parameters that are given that we're going to need to use later once we establish some equations. Then we want to establish, well, what are we actually trying to find here? And this is going to be important to keep track of kind of the whole way, because when we generate our equations, we need to make sure that things we need to find are included in those equations. And also, when we're done with our calculations, we want to just go back and make sure, did we actually find what we were asked to do ultimately? Did we actually fully answer the question? So a lot of times the find is going to look something like, what are the tension in these ropes for equilibrium, or how much deflection does a spring have for equilibrium, things like that. But we want to explicitly include it in the find because it's going to help us write our equations, and it's going to ensure that when we think we're done, we've actually solved what we needed to do. Then we can start drawing our definitely at least one free body diagram. There'll be times when multiple free body diagrams are necessary, and there might be other diagrams we need as well. Sometimes we're going to be using similar triangles. We're going to be using other types of diagrams that we can derive some equations from. But always when we are writing those equilibrium equations, those sum of force equations, those are coming from at least one free body diagram. So on the previous section, I talked about what was included in a complete free body diagram. That's what we're going to be doing in step number 3. And this is a good point to check. What are we asked to find from step number 2? If it's like a force, we want to make sure that that force appears somewhere on a free body diagram, because looking forward, if it's not on a free body diagram, it's not going to appear in an equilibrium equation. Right, so complete free body diagram, that's going to be the 3rd step. So from there, once we have that complete free body diagram, we use that diagram to write our equilibrium equations. And we are going to, for every free body diagram we draw, we're going to be able to get 2 equilibrium equations if we're in 2 dimensions. And we'll see later that we get 3 when we're in 3 dimensions. This is for particles. So for 2D particle equilibrium, every free body diagram gives us 2 equations. We're going to be able to sum forces in typically the x direction and forces in the y direction. There will be times in some examples we're going to see where we actually need multiple free body diagrams to solve everything that we're interested in. Now, probably in this section we'll encounter that less often, but in later sections we're going to be seeing that we have typically more than one free body diagram. So for each one of those, we're going to be able to write those 2 independent equations. We might get additional equations as well. If there's a spring involved, we are going to use Hooke's law. Well, that's not coming from the free body diagram. If we are using some sort of geometric equation, so again, like a similar triangle, that's probably not reflected in the free body diagram, but another diagram that we drew. And as we're writing our equations, it's going to be really helpful to number them as we go, because once we're done writing our equations, or we think we're done writing our equations, it's a good idea to count up how many unknowns appear in those equations and how many unique or linearly independent equations we have. Because that's going to be a sign, if we have the same number of unknowns as we have equations, we have established a solvable system, because we are dealing only or primarily with linear systems in this class. And this is also a good time to check what were the things we were asked to find in that find step. Do those variables, do those quantities appear in at least one equation? If not, if there's a value in the find that is not in an equation, well, at the moment, we have no way of finding it. So that might be a clue that we have to add some additional equations, whether that is coming from another free body diagram we have not yet drawn, or maybe, again, there's some geometric equation that we have not considered that's going to link multiple of our variables together. So the last step, we have looked through our equations, and we see we have as many unknowns as we have equations, and we have seen that the things we were asked to find appear in those equations. Now we're ready for the solve step. So we can solve this set of simultaneous linear equations. There's different ways we can go about solving it. Because these are all linear equations, we can use whatever we know from matrix algebra to solve it. Typically, at least early on here, we're going to see we have two equations and two unknowns, so using a technique like substitution or elimination and doing it by hand is going to be perfectly fine. But as we start to get these larger and larger systems, trying to do it by hand is going to be really prone to making errors. So in the solve step, we might go to a tool like Mathematica to help us do the algebra. So the important part is the equations we write in part 4 must be correct so that when we solve them in step 5, we are getting numerically those correct answers. And also, the step 4 and step 5, if we're working by hand, there might be times that we write down a couple of equations, see that it's solvable, and start to get some numeric values right away. And then see, oh, you know what, we need a couple more of equations, we can keep adding them, and then that's going to help us, by hand at least, solve for our unknowns. So you can go back and forth between this step 4 and step 5, but by the end of step 4 and step 5, we want to make sure that we did indeed solve for the things that we were asked to find. And finally, a check step. So this is where we can check not only our algebra or our arithmetic if we solved it by hand, but also to make sure we didn't accidentally write down maybe a wrong equation or two conflicting equations. So sometimes there's going to be multiple sets of equations that we could have written, not that all those equations are linearly independent. So in the check step, we want to think, is there an alternate way we can get equations or an alternate way that we can solve this to make sure that as a double check that the numeric answers we're getting are correct? Because if you derive another equation that should also be true, and you put in your numerical answers from step 5, and you get your equation doesn't work out, then something went wrong. Either something in the arithmetic in the solve step, or maybe you wrote your equations down wrong, or maybe even in the free body diagram, you drew something wrong, or you forgot to include a force or an angle or something like that. So the check step is really important to make sure that we are doing the correct work. Now, we're going to be going through all these steps in the examples, so this is just an outline of how all these examples and all the problems you do in this class are going to proceed in these 6 steps, starting now in 2D particle equilibrium, continuing in the 3D particle, 2D rigid body later, 3D rigid body, and so on. These are the steps we're going to be taking. It's just each of these steps is going to start to get a little bit more complicated. So a couple more things before we start looking at some examples of 2D particle equilibrium. So especially as you're starting off, selecting that object of interest or that particle interest is not necessarily obvious. What is the point that we should try to be isolating and then solving for the forces that are acting on it? Well, this is where looking at the find step is really going to be important. If we're being asked to find the tension in some specific cables, well, then the object we want to isolate is probably the one connected to those cables. Because there might be times we have different options of what object or objects we want to isolate and draw the free body diagrams of. So kind of thinking ahead that the only way for an unknown to appear in an equation is if that unknown is also appearing in a free body diagram, we want to make sure that the object we select is touching at least one of those unknown forces that we're going to be looking for. So as you get more practice, this first step is going to become a little bit easier of selecting that object. Now, in 2D, we're dealing a lot with ropes and cables attached to our object, and this is also going to be true later, we'll have ropes and cables when we're dealing with rigid bodies as well. But something to keep in mind with a rope or a cable is, one, the force in a rope or a cable must be directed along the length of that rope or cable. We're going to be seeing that this is where we start to implement that unit vector, where we're going to know the direction of the force, but we're not going to know the magnitude. And additionally, for a rope or a cable, these are objects that can only hold tensile loads. A rope or a cable can only pull on an object. It is not capable of pushing. So sometimes when we're labeling unknown forces, it's useful if we know it must be in tension to name it with a T and then some subscripts, as we'll see in our examples. Ropes and cables are what are known as two-force members. And a two-force member is really any object where the force in the object must be directed along the object itself. And we'll be seeing more of these as we go through. Now, I am going to almost always be assuming that a force, an unknown force, is pulling on our object. I'm almost always going to be assuming that a force is in tension, meaning it's being pulled apart, not pushed together. This is just, I think, a little bit easier to keep track of everything much more easily. If we just assume everything is in tension, then the signs, the SIGN signs, are going to kind of tell us if we were right or wrong in the end. We're not going to see this too much in particle equilibrium, but definitely in rigid body equilibrium. If we always assume that forces are in tension, if we get a positive answer, that's going to mean our assumption of tension was correct. And if we get a negative answer, that's still okay. As long as we were consistent, a negative answer is going to tell us that that support was actually in compression. We're going to be seeing as we go through these examples that even though some assumptions are going to be wrong that we make, as long as we make those assumptions consistently wrong, the math is going to kind of work out in the end, and we're going to know, oh, well, we made this mistake or this wrong assumption consistently. We know at the end how we're going to correct it. And we want to keep in mind, as before we even get to the equation step, when we're drawing our free body diagrams, keep in mind that in particle equilibrium, in 2 dimensions, we will only get 2 equations out of any one free body diagram. And when we get to 3 dimensions later, we will get 3 independent equations. So when we're developing our equations, we can think of this up front. Are we going to be generating enough equations for all of our unknowns? Or are there going to be other ways we are going to need to find to generate more equations? And finally, for right now, a very common mistake is to confuse masses from forces. Because in our free body diagram, we are the only vectors that we are considering that act on our system are going to be those from forces, which are not the same as masses. So a force is going to be either in newtons or kilonewtons or pounds. Typically, it could be other units as well, but those are units of force. Mass is going to be in kilograms or slugs commonly, probably not even slugs a lot in this course. Now, where does this confusion arise? Well, if we have to consider the actual weight of an object, which oftentimes we don't, but sometimes we do. If we need to consider the weight of an object, well, weight is a force quantity, so newtons or pounds typically. If we are given the mass of an object in kilograms commonly, we need to make sure that if we are accounting for the weight force acting on the object, that we are converting that mass into the force due to gravity. The force due to gravity is just the weight of the object. So we need to keep in mind kilograms should not appear in a free body diagram. That is not a unit of force. Typically what you're going to need to do is multiply the mass of the object times the local acceleration of gravity in order to get the weight of the object. And that weight is a force and will be included in our free body diagram.